So this is a movie that shows the evolution of selected isotopes in the helium-rich intershell of an HB star. Is a typical phase of a 3 solar mass star, just taken as a typical. So this is the mass. It's only a selected part of the star, of course, because we are focusing here, we're zooming in on the region where the S process happens. So we are considering about 10 to the minus 3 solar masses here. The protons are the blue line. So this is where the convective envelope, which is the gray region, ends, which is rich in protons. They also show where the helium burning shell is, because this is where they are destroyed. There is helium-4 and carbon-12. These are these two isotopes that increase just below the convective envelope, because this is the helium-rich intershell. Nitrogen-14 and neon-22 are also shown. Because this is interesting as a neutron source. Carbon-13 is the other neutron source. At the moment has very low abundance, but we will see how the carbon-13 pocket will be formed. And then there's two isotopes that are produced by the S process, barium-138, which is always produced, neodymium-148, which is produced when the neutron density is high, because it depends on the branching point, and neodymium-147. At this point of the life of the star, we are during the third Rajab. This means the convective envelope is deepening and reaching inside the helium intershell and carrying to the surface the product of burning in the intershell, for example, the carbon-12 here. At one point, we artificially introduce partial mixing here. This is the partial mixing that leads to the formation of the carbon-13 pocket, and in this particular model, it is introduced artificially by hand. So here there's an abrupt decrease of the proton profile, and in the next frame, there's no abrupt decrease anymore. The proton profiles is decreasing exponentially with mass. So this is a line because this is in a logarithmic scale. Because the temperature is quite hot here and there's carbon-12, there's a lot of carbon-12, the carbon-12 and proton react very fast and produce the carbon-13 pocket, which is, we already can see it here. So the carbon-13 reaches a abundance that is almost 10 to the minus 3 as a peak. There's also a nitrogen-14 pocket on top of it where the proton abundance was higher. So here we see that the interpulse period starts again. So we have the burning of protons here. This is the hydrogen burning shell, and just below is the pocket where the carbon-13 is already starting to burn into neutrons, and therefore we can see the signature here in the increase of barium-138. So we will see this effect that lasts quite long. It's quite of a slow process as the interpulse period continues. Hydrogen burning continues, the carbon-13 is burning, and barium-138 is produced, while neodymium-148 can only be destroyed because the neutron density is too low to activate the branching point. So we see that the carbon-13 is completely destroyed during the interpulse period. And at some point, the helium will ignite in a quite in a thermal pulse, and therefore we will have a convective region appearing in the intershell. We will see this happening. The convective region is shown as a gray area. And when the convection happens, everything is, of course, mixed up. So this is the long interpulse period. There's the convective region that appears suddenly where helium starts to burn and mixes everything up. In the convective region, all the nitrogen from the previous hydrogen burning ashes is mixed in. So there's a lot of nitrogen at the beginning, but then it burns and converts into neon-22, which is why the neon-22 increases as well. Now, the neon-22 is burning as well. This is the second neutron source that is burning at this point, but we cannot notice this in its abundance because only a few % of it burns. So on this scale, we will not notice it. But we can look at the neodymium-148, and we will see that its abundance will increase. This is because of the neutron released by the neon-22 that have enough high neutron density to open the branching point and produce neodymium-148. Then the thermal pulse is extinguished, and we have again the dredge up happening. So as at the beginning of the movie, the envelope comes in and it carries to the surface material that was previously part of the intershell and was mixed up during the convective region that developed there. Then again, we have the formation of the carbon-13 pocket as it happened previously, and the same cycle that was shown before will be repeated again several times in the life of the star.